So after yesterday, I was thinking really a lot how I can do it correctly, and I was really wanted to start from scratch today. So, it's a new year. I can start again. I want to talk about some rules, but I will not talk to you about some rules. So let me just kind of finish up what we did yesterday, saying that even if I was unable to really explain how we do some rules, I at least hope that you got the idea that some rules exist and there is a mechanism to do some rules. And one day, I hope to write something clear about this. Oh, I really wanted to. Shit, I got so confused. So what I wanted to do, I want to tell you two links. One link is that some lecture notes that we have written. It's called Just a Taste. And I wrote it with a former student of mine. He was at Cornell, Flip Tenedo, and he's now a professor in California in UC Riverside. And he has a really, really fun way of writing. I really love it. Everything, I gave the lectures and he wrote them. And it's really nice written. A lot of kind of cool jokes. So you should try to read it. And a lot of what I was saying in these lectures is much more there. So you should try at least download it, okay? At least. Okay, that's this my flavor of physics. So that's this lecture note based on a full semester course on flavor of physics that I was giving at Cornell. But even that, in this lecture, I didn't cover some rules, so it's not there, but a lot of other stuff is there. And then I was also tell you about this book that I'm writing. So I create a short URL, shorturl.au. What is AU? So the short URL coming all the way from the other side of the world, shorturl.au/PT. Anybody know what do you say PT? Yes, good. JLN. Okay, so that's supposed to be some link to the current draft of our book. It's not final yet, so you actually have a lot of power to change the future of particle physics. But give me remarks. I say, hey Yuval, there's no minus sign there, or hey Yuval, when you multiply matrices, this side should be like this. Okay, but I mean, I'm not writing it alone. I write it with my advisor, Yossi Nir, and he's much, much careful than I am. It's a whole different story. He's really, really very, very good. So hopefully there's not too many typos, but clear, if you do read some parts of the books and you do find some mistakes, please let us know. Let me know. I'll be happy to. Okay, so that was my little announcement on this. So what I want to do today in this last lecture, I want to talk about the flavor anomalies. And before we even start, let me say that some... Yes?
I just very quickly tried the link, but it doesn't work.
It doesn't work?
Both of them.
Both of them?
Yeah.
I can't believe it. I mean, how can I... So this is not... So what is the number? What is the correct number?
It's about the thermal something.
It's right in order of magnitude.
Cannot believe it. Give me a second. I cannot. It's you know why it's like really, really bad? Because the way you start.
It's 4. Instead of 7, it's 4. Yeah,
and then it's correct? No, because when you start the year, you should start like correctly. And if you start the year by making 2 mistakes on I mean, there's 2 links, and this one also doesn't work.
2 mistakes, sometimes they cancel.
So we had this can't believe it. I mean, how can it be that I make so many mistakes? I mean,
Are you sure it's not 18?
I'm not sure of anything anymore.
I think it might be 18. AT, not AU.
I tried 18 and it didn't get it.
What is AT?
What? I don't know.
Well, how can it be? Did I make? No, it's
18 something else.
Okay.
it is something. So let's. Can we do it? I mean.
I was going to say, we're actually going to be asking.
Oh yeah. Okay. I got the solution. So we're gonna have a question and answer session after the break. So I'm gonna create a new dose. I know how to do it. It's very nice. You go, you Google, you click. So then I will copy it. Forget about it. So I want to talk to you about anomalies, about flavor anomalies. And since you mentioned this, since there's 2 minus signs, I want to start with, instead of, I'm going to do a little deviation from my plan. So, it's really a disaster today. And that's just the beginning of the year. I mean, can you imagine what would happen a few months from now? For now, that's how you start your year. So, I want to tell you about the most anomalous anomaly that there is. And most anomalies, how do you, when you have an anomaly, what you usually know? You note that many people write papers about those anomalies. For example, let's say the LHC, go run, find some resonance, let's say, give me a number, 750. Give me a number. How many papers do you think going to appear? 100, yes? So that's a good anomaly, okay? And then it disappears, okay? Very good. But there's some very interesting anomalous anomaly that's happened in 2011 that almost nobody heard about it. Some of this anomaly you heard. I'm sure you heard about some anomalies, okay? So I want to ask you, and how many of you heard about the anomaly in CP violation in tau decay into K pi neutrino, K short pi neutrino? How many of you heard about this anomaly? 1? Because I told you? Yes? No? Seriously? So you're the first one, because so far all the people that told me that they know about it is because I told them. So you're the first one who actually know about it without me telling you. You know it because I told you. Sorry. Anybody else? Okay, Stefan, you know about it. Because of me, no.
Because people in my department were working on it.
Ah, okay. And they had a paper on it?
They are trying to.
They are trying to. But yes. Anyway, so the very interesting story about this anomaly is that there's basically no papers about it. There may be 1 or 2 papers that try to explain it, but basically you cannot explain this anomaly. It's a 3.4 sigma anomaly. Okay? And the story is that they measure CP violation in this tau decay. And the standard model prediction for this anomaly was minus 0.36%. Okay, that was the standard model prediction.
What's the measurement?
And then they make they measure CP violation in this decay. Okay, so they measure tau decay, tau plus decay versus. Okay, let me write it explicitly. They write ACP is defined to be the width of tau plus decay into K short pi plus neutrino minus the width of tau minus into K short pi minus neutrino. Okay, so here it's actually a neutrino bar over the sum. Okay, so they measure this rate.
So they do have a paper.
They do. Okay. And the standard model prediction is this. Okay, and then they make the measurement, and the central value of the experimental measurement was plus 0.36%. Okay.
The mistake is clear.
The mistake is very clear, right? So you look at it. So the morning the paper came out, and I look at it, I had the same reaction. So they must have some minus sign. So I went to the theory paper, talking about two minus signs. So I went to the theory paper, and I said, okay, I'll be very careful. Let me check the theory paper. I checked, and basically equation number 1, a sign mistake. Okay, it was like trivial sign mistake. Okay, so I was like, yeah, okay, that's it. But then I said, why don't we keep going? And then I kept going, and then actually it turned out that there's a very non-trivial subtle sign mistake. Okay? So we actually wrote a paper where we actually explained the non-trivial sign mistakes and said, actually the original paper had a non-trivial sign mistakes, but it also has a trivial sign mistake. So actually there's a total 2 sign mistakes, and the standard prediction end up to be the original paper.
Maybe a third one?
No, it just, so we kept working. No. So now I'm totally sure that that's the standard prediction. And then the person who wrote the original standard model paper, he gave a talk somewhere and he said, you know, I made this thing that, yeah, you know, some people, something, but it doesn't matter. You know, we still have nothing changed. So I have 2 sign mistakes. So then you always have to be very careful when you see something like this. It's not to say oh, there's a sign mistake. You say there's an odd number of sign mistakes. So, you know. Anyway, we don't know what the answer is for this anomaly. And I probably will not tell you too much about this anomaly. But now all of you heard about this anomaly and about the fact that it's actually a really cool non-trivial sign that actually entered there.
Where was it measured?
It's measured by bar. And that's very interesting because nobody kind of cared about it after. There was almost no papers. Bell didn't redo it. It's in 2011, okay, which means 9 years ago. So it's almost in the beginning of the previous decade, right? But Bell 2 hopefully will do it. Will you? Yes, thank you. Okay, we got confirmation. So Bell 2 will do it, and then we know what's going on. And if they still see it's really far away from the standard model, maybe next time we will talk about it. So, I want to mention some other anomalies that we have. And the basic point is as following. So we already I made this point many times, that the standard model works extremely well. And that's basically the fact that there's a huge amount of experimental things that had been measured, and they all agree with the standard model. The number of measurements are much, much more than the number of parameters that we have in our model. So the standard model had passed a lot of tests. Okay? And basically, within accelerator physics, everything agrees with the standard model. Assuming that we say something is disagree if it's more than 5 sigma. And why do we choose 5 sigma? So 5 sigma is the standard claim in particle physics to say I discovered something. So if I have some measurement that is 5 sigma away from your expectation, then you say I disagree with the expectation. So if I have something that is 5 sigma away from the standard model, I say I discover something new. Okay, or 5 sigma away from the null hypothesis, okay? So when they see signal for the Higgs, I don't know if you remember the big deal when the Higgs was discovered. Anybody? 2012. Wow, it's already so long ago. Wow, so then it was this big deal that they actually went to 5 sigma. So it was 5.0 sigma, they said we find the Higgs. When it was 4.9, they didn't find the Higgs, okay? So it's total arbitrary number. Why did we choose 5 sigma? I have no idea, but that's the standard. We just choose 5 sigma. Okay, you can choose whatever number you like. So that's considered discovery. So right now, there's actually nothing that disagrees with the standard model in experimental physics that is more than 5 sigma. Actually, there's even nothing that is more than 4 sigma. Okay, everything agrees up to 4 sigma. Even above 3 sigma, it's kind of, there's only very few, and it's not so clear if we can actually claim that it's 3 sigma. So the standard model works. Okay, the standard model is amazing. I know I said it many times, and I know people, you know, we had this argument about other part, but yeah, we don't understand dark matter, we don't understand quantum gravity, but within accelerator physics, within the thing that you go and measure, it works. When you do flavor physics is explained by the standard model. Okay? So then, the first anomaly, that I'm not going to talk about it for so long, was of course neutrino masses. The standard model predicts that the neutrino is massless, and you go and you do neutrino oscillation experiment, and you find that neutrino has mass. Okay?
Is that a prediction? It just doesn't include it. It just doesn't include it because it wasn't known. Is that a prediction?
So again, philosophically, you say I define my standard model to be up to dimension 4. So the standard model predicts neutrino are massless. That's a prediction. So first, I want to make one point that now after all those years, it's kind of a simple point to make, but Now when I tell you, oh, we did neutrino oscillation experiment, and therefore we know that neutrino has masses, right? But in the very beginning, when we start seeing a signal of neutrino flavor changing in neutrinos, we really didn't know. We were not actually sure that what we see is neutrino oscillation, okay? And that's something that you always, when you have something new, you always have to keep asking the question, are we really sure that the only explanation is neutrino masses, okay? And many people wrote paper, including myself, and said, maybe it's something else. Maybe it's this or this or this. And now, you are coming into the world of physics after we totally sure that we understand neutrino mass. But when I started doing physics, it was the time that we were not really sure if what we see is actually neutrino masses or not. Okay? So you have to write those papers and ask, can you do this, can you do that? And the idea is, how can we make more measurements, how we can do more analysis to make sure that the only explanation of what we see is neutrino mass? Yes?
Are we sure it's Majorana?
No, we don't sure it's Majorana, but we sure it's mass. So let me tell you the following. So how do we see neutrino oscillation, okay? So for example, we have some, let's talk about atmospheric neutrinos, okay? So we have here the Earth, here we have some atmosphere, okay? We have some proton come and hit the atmosphere. This proton generate a pion, okay? This pion decay into a muon and a neutrino, okay? And this neutrino is a muon neutrino, and then this muon decay into an electron neutrino, and muon neutrino, okay? So then just based on this, what you expect that when you come to the Earth, you see 2 muon neutrino versus 1 electron neutrino and no tau neutrinos. So what you expect to see in terms of flavor of neutrinos is 1, 2, 0. That's the expectation, okay? And what they saw initially, they saw ratio like this initially, okay? They say, how can you explain it? And one way to explain it is that there's actually neutrino oscillation and that some of the mu went into electron and then it's, okay? And now we actually know that the correct explanation is that some of the mu actually went to a tau neutrino, and the reason that here there was a 0 is just because they didn't know how to measure those tau neutrinos, okay? So that should not be a 0, that should have been a question mark, okay? That's how it should have been done back then. Okay? And the fact that we have here 1, 1 is basically because this one went to here. Okay? But we don't really know that that's neutrino oscillation. All what we know is that the flavor ratio is different than the flavor ratio that we had before. Okay? So I want to ask you a question. Okay? Let me just assume the following thing. Let's forget about tau. Let's say we didn't measure tau. And I say I start with a ratio of 2 to 1. At the upper atmosphere, and when I come to the Earth, I have 1 to 1. Can any of you come with an idea that is different than neutrino oscillation to explain this? Absorption. You've been thinking about it for so long. Yes, very nice. Where it going? What's going to be absorbed? Where?
Some of the tools, some of the electrons.
Oh, sorry. So that's mu.
Some of the neurons.
Going to be absorbed. Very nice. Nice. Those days nobody cared about dark matter.
They should have.
They should have. I know. Looking back at my history, I hit my head about how come I. But from farther out, you see. So can you build a model that actually the muon neutrino is absorbed by the dark matter and the electron are not, and that's actually explain the data? Maybe. But I hope you see the idea, okay? Anybody has another idea? So this one, I guess, yes?
Something like a violation in the process, some decay.
Some decay. So that's the first paper that people wrote after this result was actually maybe there is a decay. Maybe we have an mu decay into an EE plus some particle, which is also dark matter. But maybe the mu decay into an EE, right? So maybe that's what we are seeing, okay? So now let me ask you the following question.
Then there will be 2 electron neutrino. One is to 2. If it will decay, then it will be 1 more neutrino.
So if all of them mu decay into this, then it will be 1 to 0. So you have to make sure that this decay,
0 to 2.
the lifetime of this decay would be roughly the same lifetime. So not all of them decay, only half of them decay, or whatever, quarter of them, third of them decay, something like this.
Or you can find something to create more electron neutrinos, maybe.
Any idea?
Another particle coming into the atmosphere.
That only create electron neutrinos. So this is not the main.
Yes.
Yes? I hope, what I want you is to try to be a little bit creative. So the process of when we have an anomaly, this is the following process. The first part is, oh, there is an anomaly, and we see something new. Then we ask, can I have some new explanations? This is kind of the standard explanation now, but back then you could come with more explanation. And then once you have more explanation, say, can you actually do a third experiment or a second experiment to actually distinguish between two different explanations, okay? So now I want to ask you the following question. Let's take the decay one, the decay hypothesis versus the oscillation hypothesis. Can someone think about an experiment that you can do that tell the difference between those? So? So I would say that in both of them you start with, in both of them the muon neutrino become an electron neutrino. In one way the muon neutrino oscillate into the electron, in the other one it's decay into it. Can you just tell me what would be the difference between if the muon...
To measure the tau neutrinos?
So yes, so the tau neutrino would be one way, okay? Unless this one, if this one is tau, then it will explain the same. Yeah?
You have something sensitive to this X particle.
So maybe I can have this X particle, but if this X particle is a total inherent thing that so it depends on the X particle. So if this X particle somehow interact somewhat strongly, we can look for that. But there's other idea that I have in mind, yes?
If it oscillates, it comes back.
But there's no enough time for it to come back, but you are in the right direction. If it's oscillated, it must come back, but if it's decayed, it can never come back. And here, when we do this experiment, we only see the very beginning of the oscillation. So what we have to do in order to see the comeback of the oscillation?
From the other side of the neutrino.
Or we can look, for example, for something that have much longer wavelengths and it's come back, okay? And actually, that's something that eventually they did, okay? Or if you like, you look at the formula, and the formula of oscillation is you have some sinus of whatever with some t in it, and the decay, it's e to the minus, okay? And it's small when the width or the oscillation, when t is small, these two are the same. It's 1 minus x or something like this, some x. But this one come back and when one doesn't come back, okay? Can you think about something else that should be almost obvious just from the fact that here I have a decay and there I have...
You can look at the matter effect, I guess, because for the oscillation, the matter potential affects the oscillation, and for the decay, it doesn't really matter.
So that's true. So one thing that we could do is actually to look very carefully about matter effect, and now we know it. The point is that this is really hard because it's actually a very small effect. The energy spectrum, yeah, that's what I was after. Okay, clearly here it's changed the energy spectrum, and in oscillation it doesn't because the full things, right? And here it does change the energy spectrum, okay? And that actually was the way that they actually got out of this, okay? So, yeah. So many people wrote a lot about this. I wrote a paper where I suggest that we have violation of quantum mechanics, okay? Crazy, huh? I know. So it was so crazy that I didn't send it to a journal because it was so crazy, right? So I didn't send it to a journal. It was only on archive. And a year later, someone else wrote a paper and said, oh, it cannot be violation of quantum mechanics. And I happened to be the referee. And I say, you know, actually, it could be violation of quantum mechanics because you missed something. So I send it back to the authors. And the authors say, wow, thank you very much. You're totally correct. It could be actually violation of quantum mechanics. And then they put it in PRL. And this paper, within a year, he had got more than 100 citations. And I like, so if you have a crazy idea, send it to PRL. Okay, don't say it's too crazy. Okay. Of course, we don't think there's any chance that quantum mechanics violated, okay? But the point was that there's a way to experimentally test it. And they actually did the experiment and they got convinced that it cannot be violation of quantum mechanics and it must be, now we're kind of sure that it's oscillation. Okay? Very good. So what I wanted to give you with this example of a known anomaly is kind of the stage that we go in an anomaly, okay? First, experimentally, we want to make sure that there's nothing in the experiment that we messed up. Once we understand there is an anomaly, we try to find all the possible explanation that is valid with everything else. Then we try to find other experiments that we can do in order to distinguish between the different solutions, okay? Until we kind of down to the say, yes, that's the new solution. So when I said, oh, neutrino oscillation implies neutrino masses, it's a far from a trivial statement. I hope you see it. Neutrino oscillation only implies that we have some violation of lepton number, family lepton number. But the fact that it actually comes from masses and this is the right, is a sinus of something, that's a far from a trivial question. Things that it went a lot, like 10 or 15 years after the initial discovery, we got convinced that it's oscillation and not any other explanation. So we have to go through all those stages, okay? Now, what's happened with most of the anomalies, at some point they disappear, okay? Why anomalies disappear? They have lifetime, right? They decay, okay? Statistics. So one case is that you just statistics. You keep running the machine, you collect more statistics until it was a statistical fluctuation. Other reasons that anomalies disappear? One is, yes?
Some bias from human bias, I would say.
Human bias, or sometimes we say some systematics, or some just, we didn't really fully understand what's going on in the experiment, and we find something in the experiment. And the last way that yes?
For example, form factor and VCV, VUV, so that is...
Yeah, let me say sometimes is theory bias. Sometimes we made a theory mistake. And this theory mistake, usually it's not a trivial minus sign, but it's actually a complicated, deep thing that we didn't fully understand. And when the data come in, we understand that this disappear, okay? Now, what I want to tell you that right now, I'm doing flavor physics basically my own life. And it's probably, with some of you, I can say that I'm doing flavor physics before you were born, I guess. Right? If you were, I started, my first paper appeared in 93. Anybody here born after 93? Yeah, woo! Okay, so I'm doing flavor physics before you were born, okay? And I feel that all the anomalies that we have right now in flavor physics, none of them is real. All of them going to disappear. That's my predicist, okay? And it's totally okay to have your opinion on such things, okay? But I still believe that it's extremely important to study this anomaly and go to the process. Because the fact that I think that they are going to disappear, it's totally irrelevant what I think, okay? What is important is that you have some data and you have to go and study that, okay? So if someone asks me, and many times people ask me, and I gave many talks on flavor anomalies, and people ask me, so what do you think? I said, I believe that all of them, there's some statistics or systematics or theory prejudice that eventually will come up. None of them is truly deviation of the standard model. That's my belief. But it doesn't, the fact that I think like this doesn't tell me that I don't want to work on it, okay? And that's something that I feel as a general, as a pride of a physicist. I feel that in our field, it doesn't matter what you feel. And I see in other subject on science people, it's very important if you feel that it's right, you work on it. If you feel that it's not right, you don't work on it. We are not. I work on it. If the data tell me something is there, I'm working there. It doesn't matter if I feel that it's right or wrong, okay? Because we don't really know, okay? Just feelings, okay? Feelings are important, I know, but not, okay? Good. So what I want to tell you, I want to tell you some of the anomalies that are around, and I'm going to talk very little about some of them, okay? So here are some that we have. So in B physics, they have very nice name. We have the Rdrd star anomaly. How many of you heard about this one? Okay, not all of you. We have the RK star anomaly. Almost the same, you just changed the letter. Okay, how many of you heard about this one? It's almost the same subset. So it seems like some people heard about and some not. Then we have things like P5 prime. 1, 2. No.
You made that one up.
Of course. P5 prime. You know what the P5 is? No? Okay. So P5, it stands for the, it's some acronym of, I forgot what the acronym is, but it's basically this committee that every 10 years the US Congress assigned for you to study the future of particle physics in the US. Okay? It's a huge committee. You have to, huge amount of meetings. They asked me to be it last time, and luckily I said I'm in Israel and I cannot be. It's a year long that you have to go to Washington like 10 times a year to do meetings. And at the end you say, we think that US should now, do neutrino physics. Okay? It's kind of a very important committee. Okay? So what is P5 prime? It's the angular dependent in B2K. So this has to do with the angular dependent in B2K star L plus L minus. Okay? And it's nothing to do with P5. That's why there's a prime. Okay? So this has to do with the angular dependence of this. And actually people find that the angular dependence in B going to K star L plus L minus is 3 sigma is different than what you think is the standard model prediction. So I didn't make it up. How could you even think that I would make it up?
You can test us with one of them, so I was guessing that one.
Okay. No, nothing here is made up. VCB, issue of we're really not sure about inclusive versus inclusive VCB, inclusive versus exclusive VCB. There's actually more. There's in charm physics, there's the problem of CP violation in charm, that some people think it's an anomaly, and we don't think it's an anomaly. We actually think that it is actually standard model. So, but since some people think it's an anomaly, some people talk about it. And I really want to talk about it, but I don't think I will have time.
So is it delta ACP?
Delta ACP. Yeah. It's called delta ACP.
So this is the one that Yuval of 2020 doesn't think is an anomaly, but Yuval of the...
Yeah, I know.
It's predicting this result.
Okay, so... oh, yeah, you're right. So let me kind of... Gilui naot. I don't know how to say it in English. Gilui naot, how would you translate it to English? When you have to confess. Okay, so let me confess, okay? So I think in 2007, we wrote a paper, and I think, I'm not sure if we were really the first, but we were definitely one of the first to actually consider this decay and why it's kind of important to do this analysis, etc., etc. And in the paper we say, if you're going to see it, it's going to be new physics. And the people who actually did it are people from LHCb. And in 2008, I think, they invited me. They have like a collaboration meetings, and every time they ask for one theorist to come and tell them what they think is the most important thing to do. So I came in 2008 to LHCb, and I gave a talk about CP violation in charm. And I said, one thing I can guarantee, if you're going to measure it, it will be new physics. No question asked. Okay? And that was the end of, the summary slides. Okay? The summary slides was that. Okay? And I still have these summary slides. They said, no question asked. Okay? And then they measure it, and I reevaluation it, and I'm sure it's standard model now. Okay? So then I went to LHCb. Again, they invite me. I came. I gave a talk, and they are Yuval. I do remember you saying. So now we spend all those years because you told us that no question asked, and now finally when we did, I said, sorry. So we change. Things happen. And, sometimes maybe you should not be so convincing, because I like to say, there's a big, I tell you, the standard model is not specific. It's not specific, but, so I was very convinced. But now I totally changed my mind in the following sense that when the result came in, I spent probably a little more time thinking about it, and I understood other things. So these are then those anomalies that we say we have theory bias, and that was definitely my own theory bias on this, okay? And I don't know what the rest of the community, I think right now it's about half and half. Some people agree with my new me, and some people agree with my old me. So I have a super position. But no.
How you measure about this ACP in charm system, like what percentage it should be in standard model, just not from the parameterization of the K matrix?
So I think, maybe we'll have a little time to talk about it, but it's at the end of the day, it's just the hadronic uncertainty. And I think I underestimate the hadronic matrix element. And now, based on a few other observable, I'm almost sure that I underestimate the hadronic uncertainty before, and I actually feel that the hadronic matrix element I know much better. We can talk about it after, okay? Anyway, and the other one, there's some B physics, and there's also some Keon physics. The most exciting one is one that appeared a few months ago. It's the Co2 anomaly. How many of you heard about the Co2 anomaly? The same subset, okay? So there is a look into K long, into pi neutrino, anti-neutrino. And they saw some event, and they should have seen something like 0.02 event. What does it mean that you should see 0.2 event, okay? You either see an event or not. That means the expectation value of the number of events was something like, I don't remember the number, but much less than 1. And then they do blind analysis. They look it up. They open the box, and they saw four events inside the box. But the expectation was much less than 1, okay? And they did not claim a discovery. They just say, we opened the box, and we saw the events, and we don't know what it is. Because there's actually quite a very strong theoretical consideration that says that it cannot be this decay. And I want to talk about it because I really excited about it, and because I was invested in it for a long time, so I kind of like it. And in Keon physics, there's also, Keon and pi physics, there's also the so-called the Cabibbo anomaly, theta Cabibbo anomaly. How many of you heard about the Cabibbo anomaly? Yes, Stefan, good. Okay, so this one is less known, okay? Even those who heard about all the others, you know about this. So I hope I will have some time to go. It's okay, the clock? No, it's not.
No, it's an hour.
Okay. Okay. So what I want to do, I want to go briefly on some of those anomalies. I'm not going to like spend a lot of time on each of them. But what I want to do on each of those anomalies is kind of go through the process of are we sure we understand the experimental? What are kind of possible explanation? Are those explanation already ruled out from some other cases? And if not, what other measurements we can do in order to test this versus this explanation? Is that clear, kind of the process that we have to go through? Yes?
If I may, another question. Since you have a lot of anomalies, how can you, from your point of view, decide which anomalies are interesting or which are just, you know?
So all the anomalies are interesting. Okay, yes, so if I have time and I had 20 graduate students, each of them will work on another one, seriously. And then just given the time that you have some limited amount of time and graduate student, you just choose which one to work on. And actually, right now, I don't work on any, okay? And some of them you think about, and then someone else write a paper and you say, you know, he did everything, I don't want to do this, okay? We actually, me and Stefan and Emily, we just put a paper on this anomaly, we made a small point about this anomaly. Okay, so now I know a little more about this anomaly. This one I clearly work, because some anomalies is just personal, you know. I worked on this for so long, so it's like my thing. And this one is also like, I work on it for so long that I'm excited about it. And it's very personal, okay? And this one I never worked on. So even now I kind of didn't go there. But I don't think, it's not because this one is more important than this one. All of them are something that you want to understand what's really going on, okay? And you get a deeper understanding of physics just by going and look around. And you don't know which one of them eventually will be real. And as I said, right now I think none of them, but I really like to work on all of them. Okay, so we'll start with the Rdrd star anomaly. And the idea is as following, okay? So it was first done by Babar, and what they did, they looked for the following ratio. They look for Rd. So this notation, when I have the star in parentheses, means that it's either with a star or without a star. So Rd or Rd star is defined to be the branching ratio of B going to D or D star tau neutrino over the branching ratio of B going to D muon neutrino, okay? And the point is that this ratio is supposed to be very well calculated in the standard model. Why? Because it's just lepton universality. So what lepton universality, the big point of lepton universality that I made before, what it tells us about this ratio? So I'm asking you guys, what do you expect this ratio to be? Barring phase space 1, or say it another way, you expect it to be the phase space of B to D tau versus the phase space of B to D mu. Okay? So you expect that the matrix element, the amplitude, should be identical, and then the only difference between those two is phase space. Are you with me on that? All of you? Yes? Okay, so that's a good approximation for the expectation. Can you tell me what else there is? So to a good approximation, I just said I don't care if it's a muon or a tau. The only thing I care about if it's a muon or a tau is phase space. So that's why we get this. But there's a little more. I want you to tell me something that we actually talked about yesterday. What else?
The distinction between the electron and muon.
So actually here I just call it a muon. It could be an electron, but let's assume for simplicity that I only have a muon and a tau. So there's also a lot of things to do experimentally. But I don't talk about now about experimental analysis. I'm just asking theoretically what else this different is. So it's ratio of phase space. What else? Form factors. Yes. Why? Why the form factors don't cancel? So one thing that is very important is, of course, this is hadronic decay, so there's some form factors, right? We talked about it yesterday. It has to do with the fact that I have mesons. But why they don't cancel? Because this one, so let me write it. There should be also the form factor in B to D over the form factor. Nice. Haha. Yes. But I told you yesterday that the form factor is a function. It's not a number. So it's a form factor of q squared over q squared. And you have to do some integral. And the integral is over all the phase space, right? So it's not a trivial phase space function. It's actually a convoluted integral of phase space time form factor of q squared, some dq squared. Okay? So it's not a trivial integral over phase space, so the integral of phase space is easy because it's just masses. We know the masses, right? The form factor, however, we don't really know. Why we don't know them? Because they had to do with hadronic physics, and we have to know the wave function of the hadrons, etc. So we don't really know the form factors. Okay. Yes?
And you have an additional form factor which is just the electron mass.
Yes. So it's not only the integral, there's actually a little more going on because some of those form factors, they can have also some explicit dependence on the mass of the lepton, okay? Which is actually, it's not just, I'm simplifying it by saying it's only q squared. It's a three-body decay, so you have more than q squared. In a three-body decay, you actually have two independent parameters, not only one. Anyway, the point I want to make is that it's a different phase space, and the integrals are such that we also need some form factors. Okay? So maybe we don't know the standard model good enough because there's some hadronic uncertainty. So now come the hand wave arguments, the whatever, and people say, how do we really know this ratio of form factors? Do we really understand it? Do we really trust things like isospin symmetry that I was talking about yesterday that I was not really able to explain? Do we actually understand very well heavy quark symmetry that I only mentioned that actually used to calculate those form factors? Okay? And basically everybody who ever did something on this field went back and redo their calculation. And the consensus that come out from all the people who did it is that the theoretical error on our understanding of the form factors are much, much smaller than the experimental error. Okay? So people say, maybe we underestimate the error by 5. But still, the claim is that we know this ratio quite good. Okay? So here I'm kind of make one jump. It's an important point, and I tend to believe those people who said that we totally understand this. Okay? I didn't really work on this, so I don't know the full details. And then they went up and did the measurement, and the measurements are such that if you take this form factor and phase space into account, you find that in D and D star, both of them are roughly 3, 2.5, 3.4 sigma away from the standard model. Okay? And there's also some correlation in the measurements, etc., etc. But at the end of the day, you find that these decays, the B2D and B2D star tau, is enhanced by 20 or 30% compared to what you expect. Okay? Good. So let's make the following assumption. And the assumption is that this is correct. Okay? The assumption is that really, experimentally, we find enhancement of B2D and B2D star. So that's how we approach an anomaly. We say, let's assume I trust my experimental friends. Of course, they keep trying to find their, statistical and systematics and biases, etc., etc. But we as theorists, we say, well, let's assume that this is correct. How can we theoretically enhance B2D tau? So can someone come with an idea how to enhance B2D tau neutrino? Enhance.
You could also reduce the other decay, right?
Totally. So there's two things you can do. You can enhance this, reduce this, or do both. Okay? So that's kind of how you approach an anomaly. You just say, oh, what could go wrong? Okay? It's either this is up, this is down, or some combination of them. Okay? So why, and that's, unconscious bias that I have, why did I say enhance the numerator rather than suppress the denominator? Why it's easier?
Because that's what they did.
No, I work on this decay only in the last stage, the stage of what else we can measure. Okay? I didn't actually do this kind of thing. So why Yonit caught me on this implicit bias that I had without.
You want to change the third generation?
Constraints on this. So it's the same for muon and electron channel?
Well, I don't think that we don't really know very well that it's the same for electron and muon, but we can change both electron and muon. So one answer is that, if you do it here, you have to change both electron and muon, and here I only have to change tau. That's one answer. It's easier to add diagram. You are as biased as I am. When I add a diagram, the relative sign could be plus or minus. I mean, why the sign should be plus?
Plus is prettier.
Plus is prettier. Yeah, that's right. Yeah. So I think the answer is that in general, we know much less about taus than you know about muons. Okay, so actually, we study the muon much more than we study the tau. So if you better mess up with something, mess up with the tau. The muon, it's already, it's so well established, you don't want to touch it. The muon, I know everything. The tau, so you think, internally say, we know less things about the tau than the muon, let's mess up with the tau. Okay? But what I'm asking you is let's make the assumption that what we see is enhancement of B2D tau neutrino. And I'm asking you, how can you come with the simplest new physics model that do it? And don't worry now about any other constraint that you have from other part of the theory. What can you come with a simple, very, very simple, which will be probably ruled out, and that we're going to discuss after, that do it? From your understanding, your basic understanding of how we build the standard model. Yeah, so that's kind of what people eventually is doing. They said, we have to add more particles to the standard model. But actually, for me, the simplest way to solve this anomaly is to not adding any new particle to the standard model, and I can very easily solve this thing. So I have to violate lepton universality. But how? Yes?
Make the coupling flavor dependent?
Make the coupling flavor dependent. Really nice. All I need to do is change the coupling from the W so that it's coupled to the tau a little more. Can you tell me how you can make the coupling to the tau stronger than the coupling to the muon? What would you have to add to the standard model in order to do it?
Make it mass dependent?
Yeah, but how? Now I ask a very specific question. So what we need to do, we very nicely come to the idea that so the coupling to here I have W coupled to a muon and a neutrino. This coupling is G over square root of 2. Okay? And let me do this, the coupling of the W to tau and neutrino. Let's take Just for the sake of it, let's make it g instead of g over square root of 2. It's roughly, maybe it's not really explain the data, but definitely go in the right direction. Okay? So how would I do how I move the g over 2 to g? Anybody has a very simple idea how to do it? It's ruled out. What I want you to do is to tell me how to do it, and then we'll discuss why it is ruled out. Yes?
Maybe make the Lyman rule mass dependent.
How? I mean, what I'm asking you is this idea that you remember how we built models, right? We had a long discussion about it. You define what your fields are, you define their representation, you write the Lagrangian, and then you get the Feynman rules. So how can I change my input? How would I do a different input that I will get here a g instead of g over square root of 2?
And another millimeter.
Change the representation of what? Of
Third generation.
of the
Third generation.
of the
Third
of this one. yeah, I know. So how would I change the T3 of this one? So this one, what happened here in this is the T3, right? So this one was square root of 2 is just, How would I do it? How would I change it? By some factor. So instead of being a doublet, let's say I put the tau is part of a triplet. So if the tau is part of the triplet, the charge would be bigger. This coupling would be bigger. And if I don't want to make it like much bigger, I can say that tau is actually a superposition of a triplet and a doublet with some triplet combination. Okay, so I add some other fields to the standard model and put it together. You see? So that's the way we start doing model building. We say, I need it bigger. Let's make it higher representation, so the coupling would be bigger. Yes? Okay, so let's assume that we put the tau part of a triplet. Okay? So the triplet of, I want the tau to be part of a triplet, and it should have still a charge -1. So let's have, the tau would be something like I have neutrino with a charge 0, a tau with a charge minus, and I should have another part of the doublet, of the triplet. Let's call it, this is your chance. It don't happen often to have a new particle that you can decide the name. -2. Anybody? It's your chance. First come, first serve. The first person who called that particle will be called after you. Stay. But it's ruled out, the particle. IA. II. The EIIS.
Very catchy.
Yes?
Apparently, yeah.
Very nice, the EIIS. So the question is now that we have the EIIS, okay, and it's have a charge of -2, okay? And it's coupled to the tau and the neutrino, okay? And my claim is that this particle is actually ruled out. Can you think about a reason why it is ruled out? It's too long of a name. That's how do you like the upsilon or the?
It's massless.
Is it massless?
I can think of a number -2.
There's a tau decay wave.
It must be massless.
Let's add something.
Let's add something. So let's add something. No, yeah, I think you're right. That's already. But if it's massless, how it's make it ruled out?
And how is it made to
It can be ineffective.
Oh. I really like it. That that you go to like, no, it's totally right. You go like to this such complicated way to exclude. Can I make a joke, but not? Of course. Okay. So, yeah. Okay. So this guy went to his friend, and his friend said, I have this two cows, okay, and one of them is this and one of them is that. And he said, I cannot really tell the difference between those two cows. He said, look very carefully. So the guy go and measure the length of the tail and everything. And then after, after 3 days, he said, I found one cow has in the ear, okay, the ear is 1 centimeter longer than the other one. He said, which one? He said, yeah, the white cow is much longer than the blue. So how we clearly, easily exclude this one? What would be a clear, where we're going to see this one? In colliders, E plus E minus should go to ion pair, right? Yes, and we just don't see it, right? And if it's massless or close to massless, we just cannot see it, okay? Just the fact that it's coupled to all of those. So just basically the fact that we don't see it in E plus E minus collision exclude this possibility, okay? So we already learned something very important. We cannot mess up with the symmetry assignment of the tau lepton. The tau must be a doublet. It could have a very, very small mixture of a triplet if this triplet is extremely heavy, so it's avoid all the bounds. But you already see how we are kind of go to the corner, okay? We cannot really make this easy solution. This is the easiest solution. Oh, just change the coupling. That's it. But it's already constrained from, say, E plus E minus, and we cannot do it. Yes?
Could you add a discrete symmetry?
So the point is that since this one is part of a irreducible representation, if I forbid something from here, it will also forbid those two, okay? So basically, you can try, but at the end, it will not work.
Oh, no, I mean before you even add the additional part.
This one.
Yeah, before even there.
Yeah?
You gotta add a discrete symmetry.
For what?
Preference couplings to the tau over other.
So the point is that this is just, it's basically this coupling is immediately determined while you tell me the representation of the tau. So we know that tau is part of a doublet. I know it's G over square root of 2. If this particle is part of a triplet, I know what it is. If it's a superposition of a doublet of a triplet, I know what it is. It just immediately comes from how much doublet and how much triplet you have in there. Okay? Yes? Oh, because if I have a particle that has electric charge -2, it's coupled to the photon, right? So then I will have this diagram. E plus E minus with a photon coupled to the minus minus and plus plus, right? I will have this diagram. Yes?
But you can make them really heavy beyond the currents in the
So how far I can actually make them? How heavy I can make those particles? So we don't really actually know what their masses are, right? But if they are a triplet, then we know that they take part of the weak interaction. So I cannot make them extremely heavy because they do have some contribution to the weak interaction. So I mean, I'm not going through the whole process of why it is excluded. But the feeling should be that if you have a particle that is charged under the weak interaction, and you don't have, it's not a vector-like particle. So vector-like particle can have, but if it's a chiral field, so you get some mechanism that give it mass through some Higgs mechanism, it's going to have mass much higher than the weak scale, okay? And so we would see this kind of particle, we would see them at DLHC, we would see them at E plus E minus, okay? So I'm definitely not going through the whole exercise. I just want you to have the feeling that a lot of things we already know from a lot of other constraints. Yes?
I have another solution.
Yes, please, go ahead.
And it will do both things. It will increase the denominator and decrease the denominator.
That's actually very good.
So, for some reason, the mu turns to tau.
The mu
Turns to tau.
turns
Turns
into tau, yes.
tau. So you'll see less of the denominator and more of the numerator.
Yes, so actually that's maybe the right solution that experimentally they think of tau, they think of some mu as taus. That might be the solution. That the tau identification is not very correct and they actually sometimes misidentify mu as a tau. That's a misidentification experimental issue. But theoretically, how can you theoretically actually turn a mu into a tau?
Somehow.
Somehow, yes. So that's actually a very good starting point. But then the problem is how to solve the somehow. And that's where we say the devil is in the details. Okay? So one day I was thinking I want to be a politician. Why? Because politician can say somehow we're going to have everybody going to have a lot of money and you don't going to have to pay taxes. You're going to have, everything will be great. Okay? And then you say, but how are you going to actually have this health insurance without taxes? Somehow, yay! I'm going to vote for you. Because I asked you, like, how are you going to do it? Say somehow, so, So I want to be a politician one day, but until then, I'm still a physicist. No. I'm not making a joke of you. I'm making a joke of the politician, if you didn't notice. Okay? So what I'm just saying is that that's how we are. And when we start doing model building, that's exactly the way we go. We say, let's assume there's something, and then we zoom in about the thing that we still don't know. And it's actually totally correct to say, this part I still don't know how to do. As long as you very clearly identify and say, that I don't know how to do, and it might work or might doesn't work. Okay? Yes. Yes, so the point is, that experimentally, what you are telling me is that experimentally maybe we don't fully understand how to do it, right? And that's... But that's theoretically. So what I'm saying is theoretically we think we understand this form factor. Now the question is how experimentally we detect taus. That's probably where the problem is. That's my feeling. Because it's extremely hard to detect tau. Taus decay hadronically most of the time, and it's very, very hard to identify taus. And we hope we understand it, but we are not so sure.
But that's not part of the theory?
No. So the point is that ideally, you would take it from theory. But in practice, you cannot take it from theory, so you have to take it from your data. And say, I look at tau decay in one place, and I use the data of tau decay in my place and plug it into my Monte Carlo from another place and to the analysis. But we cannot actually calculate tau branching ratio. We cannot calculate from scratch because it's hadronics, so we don't know what to do.
And the decay part is completely decoupled from the...
So in principle, you have to know the hadronic decay, the hadronic branching ratio of the tau because you reconstruct the tau. So if you see tau decay into whatever k pi, and you say, oh, now I see a tau, you have to know what is your sensitivity to this and what would be the branching ratio, and you add it up. So what I want to say is the following. There's huge amount of experimental work that go here, and there's good chance that somehow, somewhere went wrong in the experimental analysis. But what I want to do is I want to make the assumption that the experimental is correct. And of course, they do keep trying to see what went wrong there. They don't stop. They don't say, yeah, I know I understood everything. They try. But from the theory part, I'm just trying to do this. Okay? No, so can we change tau decays? That's what you are saying. And the answer is that I say this solution of changing tau decays wouldn't work because you take tau decays from other places. And now one idea would be that you say, oh, we make the assumption of factorization. That is that the tau, the decay here, I don't care how the tau is produced in this decay. And that's a very, very, very strong something very well established in particle physics. That I don't care if this tau is produced in B decays or it's produced in Z decays or it's produced in E plus E minus production. Okay, so let's go on. Yes?
In these decays that have neutrinos, how do you identify the decaying particle?
This B?
Yeah, how do you know it was a B?
So it's the usual thing, So, so let's talk for about how they know it in Baba and Bell. Okay, they use on, it's a whole different, you can tell much more. But, for example, you use it on the so-called sphericity. How much spherical the event is, okay? So if you have E plus E minus go to something that is not a B, it looks like 2-jet event. If it decay into a B, it looks much more spherical. So you run some neural network that tells you what is the probability that this one is actually a B. Okay, so that's one example that you actually know. And in LHCb, you look for another B. You look for some other B on the other side. Say if I have one B on one side, then I should have another B because in QCD, glue create BB. Okay, so I want to keep going a little bit here, and I want to ask you now the following question. So let's assume that there's something new. We don't know what it is. You have your model. People write some models that actually works. They add some other particles to the story, and B2D tau nu is actually enhanced. Okay? Can you tell me, can you think about some other things that should happen? So now you go to the third stage. So the first stage was, can you come with some new idea? The second stage is to ask if new idea is alive, and all the idea that we came from in today were dead because we look only for simple ones. But there's some example in the literature that are alive. That is, there's no other constraint. Yes?
I'm just wondering if we have two neutrinos which are massive and one which is massless, if this could change. For example, electron and neutrino would be massive and tau would be massless. If this could.
So actually the point is that in this, we know that the neutrino masses are less than electron volt. Okay, so the neutrino masses are totally irrelevant for this decay.
Yeah.
So
But
I don't
have
think.
the Majorana term and
Yes.
this changes the coupling maybe a little bit, but I'm not sure.
I think it's just much too small.
Ah, okay.
That's my feeling, but
But it's suppressed by the mass. And
that's my intuition. But what I want to say is that, if you have something and you go and work out the details and see, if most of the time your ideas die quickly. And that's something actually I want you to not to be, I don't know how many papers you already written, but I remember when I started doing my master, I had this really, really cool idea on Thursday night. And he needs the weekend, Friday, Saturday. I didn't do anything the whole weekend. Sunday morning, I was waiting for my advisor like this in front of his office. And look, I have this. I got in. I explained it to him. After 1 minute, say, yeah, but it's wrong. Say, no. He said, yes, I know what is wrong because I thought about it before and I tell you why it's wrong. 1 minute. And it was wrong. And I was like, and then he told me, he's very good. He's really, really good. And he said,
I'm trying to understand this point. So you are saying that it is heavy neutral.
one thing, let me finish the story. I want to really tell you a little story. Then you'll tell it. So then he told me this, and I really remember it. And he said, almost all your ideas are either wrong or done before. Okay? And on very few of them are not. And then he told me, don't worry. One day, I'm sure soon you get one idea that is not wrong and that wasn't done before. Don't worry. Okay? And yes, so I had some. But most of my ideas are either wrong or done before. Okay? So don't worry. Okay? Even if your idea is wrong, don't worry. It's either wrong or done before. So, when you have a new idea, keep in mind it's either wrong or done before. But keep going, and maybe it's not. Okay? Yes.
No, I was asking if there is a heavy neutral lepton that couples strongly to tau.
Yes.
Muon, so that should enhance the branching ratio of B2D star tau nu.
That's right. But nothing. So you say, let's have some other things that couple it. Yeah, and that's kind of in the spirit of what people are doing. But there's a lot of other constraints. Okay?
I was thinking, if we look at the missing mass, since it's heavy neutral lepton, that should have mass, but I don't know how experimentally we can see its.
So it will change the spectrum.
Yeah.
Okay, and the point is that you don't really see the whole spectrum. So experimentally, what you really do, you measure some part of this, and then you kind of assume that you understand to actually this. So there's so much more on this, yeah? But let me go on. We can talk much more after, okay? Let me go on. I want to ask the following question. Let's assume that this is enhanced, okay? Can you think about other things that should be enhanced that may not be measured so far? What other processes should we might be able to see?
With the same underlying quark level.
Yes. So let me make the following assumption. Let's assume that this is a knee left, that this is our well-known left-handed neutrino. So now I'm asking a model building question, okay? So we know that there's some operator that some new operators of the following form, right? Because I know that there's some enhancement in big going to C tau neutrino. So there's some new operator in this form, okay? So now can you tell me what could be I should put some L and R on here. How many L's and how many R's I can put here? Just based on Dirac algebra and stuff like this. Can I put 3 R's here?
You needed the one L to cancel the neutrino.
Yeah. So why I cannot put? So what I'm asking, can this be the form of this operator even initially? No. Okay. Good. There must be at least one more L here. So there might be all 4 L's or 2 L's, right? So for example, let's assume that I have here another L. Yes? So if I have this operator, what other operators should I have? Since this is part of a doublet and this is part of a doublet, so you know there's actually some bar here or something like this.
Also like the top left?
Yes, so I should have a top left, C right, tau right, and then this one will be a tau left. Yes? So I'm going to have something like this, right? Yes? Do you see? Because this one is the SU2 partner of this, and this one is the SU2 partner of this, because this is part of a doublet, and this is part of the doublet. I should have this operator as well. Okay? So then I can take this operator and say what this operator can do for us. Okay? You see?
You wanted to write a neutrino, right? In the
This one, no, I really wanted to write tau, because this is the SU2 partners of the neutrino.
okay.
Okay, so if here I have the SU2 partner of this and the SU2 partner of this, because it must come from a doublet. So the UV operator that I have was something like this.
Then you can change in the same way the middle ones?
Something like this.
Tau?
It depends. They are right-handed, so they do not have a partner. But this is the underlying operator, and when I open it up, I have both. Okay? And in particular, for example, this T right is not part of a mass eigenstate. It's part of the interaction eigenstate. And when I move to the mass eigenstate, there should be also some combination of C. Okay? So there's some combination of something like C left bar, C right, tau left. Okay? Something like this. Okay? And these kind of things would affect, for example, something like psi going to tau. This kind of an event. Okay? So I'm not going to get into the full story here. I don't have time. But what I want you to kind of appreciate is how once you kind of say, oh, let's assume that I find this, how I actually go from and doing some model building to find other operators and then use those operators to find some other things. Okay? Okay. So I don't have too much time, so let me just go over one more anomaly that I'm really excited about. And I'd be happy to talk much more about this afterwards, and we have question and answer, and I will try to be here also next week, so, you know, during the break we can chat also. So, what the time? Is it correct?
I think about 20 minutes.
Ah, okay.
20 minutes.
Okay, good. So I want to talk a little bit about the Co2 anomaly. And as I say, in a way, it's not such a big deal because experimentally, the experimentalists, they did not claim a discovery. They didn't say that they saw. So let me just remind you, this has to do with k long going to pi nini bar. And the experimentalists themselves, they didn't say that they saw it, which means that they themselves don't feel that they totally understand their systematics. So we as theorists should not like jump and say, yeah, you know, but still, there is something, so it's a good idea to start thinking about it. Okay? So I want to go a little bit into this, the story of Co2, and it's kind of connected basically everything that we've been talking in these few lectures. Okay? So the idea is that you look for this decay k long to pi nini bar, and in the standard model, it's calculated extremely precise. Okay, we know the branching ratio with an error of about 1% or even less. So we know it much, much better than we can hope to measure even in the next 30 or 40 years. Okay, and how do we do it? We look at this diagram. So what is a k long? Actually, I should have asked this first. You know? K long. How many of you know what the K long is? Less than half. Okay, so let me discuss what it is. Okay. usually the problem is something that you are so used to it, and I didn't think that I have to get into this discussion. But I'm asked. So the point is as following. When you look at the kaon system, you have a K and a K bar. Okay? What is a K? K0 and K0 bar. That by now we should all know. What is a K? What is the quark constants of a kaon? S and D. Where the bar goes? So there's only two options, either on the S or on the D. Okay, so I told you it's like this weird, wrong intuition, and a K bar would be SD bar. Okay? Now, these two eigenstates are degenerate. What guarantee that they have the same mass? What symmetry? CPT, yes. When it comes to theory, we all on S. CPT guarantee that particle and antiparticle have the same mass. But you also have the weak interaction. And the weak interaction actually, there's an amplitude that can get you from this to this. Okay? So there's actually coupling between those two states. And therefore, you can actually generate some splitting between them. Is it clear? Just the normal standard degenerate perturbation theory. If you have two states that are degenerate, but you can have a perturbation that actually couple them, the energy eigenstate are split. You remember this from perturbation theory? Okay? And if you look at the Hamiltonian and you have two things that are degenerate, okay, we have E0 and E0 here, they are degenerate, right? But if I put here some very small coupling, what would happen? The degeneracy will be lifted, okay? And what will be the splitting? So let's assume that epsilon is much smaller than E0. What will be the splitting? Roughly order epsilon? Yes? And what will be the mixing? So the mass eigenstate, what would be, how much I need to rotate from the original basis to the new basis? 45 degrees, okay? If you don't feel two by two matrices, you should feel like this, okay? You should really feel like this, okay? So in 2 by 2 matrices, one really cool thing about it is that you know that the sum of the eigenvalue is the trace and the product is the determinant. So you know that the sum is E0, the determinant is this minus this, right? So you know that the two eigenstates are almost E0, and the difference between them is proportional to E. And the mixing angle, if you don't remember this formula, anybody remember? So let me write the general formula. A, B, B, C, okay? Real, everything is real. What will be the mixing angle? Tangent of 2 theta equal to? Nice. Okay. So you should remember this. Okay, this is very useful. So in particular, what you see from here immediately, that if A is equal to C, tangent 2 theta diverge, so theta is 45, because 2 theta is 90. Okay? So 2 by 2 matrices, we should have the feeling, you know. When you see a 2 by 2 matrix, you just, you know everything about it. So this is kind of the formula. So when I have a very small off-diagonal term, I get 45-degree rotation. And the two mass eigenstates that I get out of them, I'll go by the name of K long and K short. K long and K short are basically K long and K short, K long and K short. No, I should not write it like this. K long and short are basically K plus minus K bar with some normalization factor, okay? And there's some CP violation, there's some a little bit story, it's more complicated, but to leading order, K long and K short are just the mass eigenstate of this little perturbation, okay? So experimentally, the mass eigenstate are either K long and K short, and we could do the experiment also with K short, but in practice, both of them are extremely hard, but this one is somewhat manageable. With K short, we could not do it. So to any practical purposes, you can just think about it as a kaon decay into pi nini bar and forget about this, okay? So what would be the diagram that give me K to pi nini bar? Is it flavor change in neutral current or flavor change in charge current? Neutral current, that's why it's a rare decay, okay? So I have an S decay to a D because I have a kaon decay in the pion. So a kaon, when it decays to a pion, the S become a D. And I should have here something that emit a Z, and the Z decay into 2 neutrinos. That's the leading order diagram, okay? And what is this blob? In the standard model, this blob, so I'm zoom in into here. And it should be something like this. S, D, and here I have U, C, and T in the loop, and the Z. Okay? And it's turned out, and I'm not going into all the details, that the top is the most important part in the loop in some way. So then what CKM matrix do I have here? If here I have a top, the CKM matrix as I have here is VTD. And VTD is one of the smallest one. Do you remember when I put the Wolfenstein parameterization? So this is VTD is what powers of lambda? Yes. Now it feels really good. Okay? So this is a small element, so it's hard to probe. So that's also tell me that this rate is very small, but it also tell me that I'm sensitive to something that I really like to probe. Okay? So you can actually calculate this diagram, and people calculate also correction to this diagram, and we know everything. Okay? It's very, very nice. What we are missing? What we are missing? So if I, yes?
Yeah, I think you can do box as well.
Yeah, you can do box as well, and actually it's a little more interesting in the sense that it's not gauge invariant. You have to do both to get invariant, ta-ta-ta. Yes, so there's a lot of cool stuff, but to leading order, this is kind of to get the feeling. But there's still something very important missing here. What do we miss here? What the other ingredient that we need that I didn't tell you? The form factor, the hadronic matrix element. So I need to know the k-on with some operator pion form factor. Yes? Any idea how do I get it? Any idea where I will get it from? Yes? I told you yesterday.
K2 pi mu nu.
K2?
Pi mu nu.
K2 pi mu nu. Okay, so why I can use this one? Because of isospin symmetry, I can actually use this one to plug it into this, okay? And then using isospin, I actually know the hadronic matrix element. That's kind of what I was hoping to get yesterday, like the importance of using the approximate symmetries of QCD. And since I know this, and I know how to calculate this from my Feynman diagram techniques, I get sensitivity to things like VTD, okay? And I can actually look and measure this decay, okay? Good. So, yes?
Is there any other channel in this process?
If there's any other channel?
Yes.
What do you mean?
Like SD and U channel?
Oh, no. So not on this one. There's actually more diagrams. So, this is just the Z exchange. There's also the so-called box diagram, okay, where these are two W's exchange, okay? But for the Z, there's no, in the standard model. So then you can actually do one other thing. And instead of measuring K long to pi nini bar, you can measure K plus the decay into pi plus nini bar, okay? And so for that, there's another experiment, which has has a very meaningful name. Even Co2 is not so meaningful, but at least it sounds nice. Na62. I hope nobody hears anybody. I don't want to make... But I think that's the last experiment that's have a name that sounds like this. Now the new experiment, everybody has a real name, like Co2.
Na64.
Hmm?
Isn't there an Na64?
I don't think there is.
Yeah, there is.
Yeah, I just don't know if they name themselves prior or post Na62.
So no, so it's a very interesting like naming schemes about how they do it, and they have E391 and all these kinds of things. So actually Na62 go and do it like this. So these guys are sitting at CERN, these guys are sitting in Japan. Yes?
So with two neutrino final states, how do you measure this? How is this?
Oh, it's extremely hard. Okay? I mean, basically what you do, you create a kaon, and you hope that you know that it's a kaon. Then you see a pion, and you see some missing energy, and you say, oh, this missing energy is neutrino. So this is extremely hard measurement, okay? And this is even harder, okay? Because the branching edge is smaller, and dealing with K longs are harder than dealing with K plus. K plus is at least, you can put a magnet and put them around. This one, there's nothing you can do to them.
Why was it this instead of K to pi EE or any other thing?
Very, very good question. Thank you, Eric.
That wasn't planned.
So I asked Eric to ask me the question. Why are you doing it with neutrino? Do it with electrons. Neutrinos are hard. You know, I told you the story with the cows, right? Right? It's the same. You do it with neutrinos, do it with the electron. Why instead of this, let's do K plus, go to pi plus E plus E minus. And where I have the Z, instead of putting in the Z neutrinos, I put in the Z electron. It's totally the same. So why I'm doing it with neutrino? Very good question, Eric. Very good. Really. So actually, there's a little bit of a difference because this one have only left-handed, the electron have both. But you know, these coupling are so well known that we can, it's a trivial thing to change them. What is really the difference? That's why this one is very interesting and the people are looking at it, but it's clearly not as interesting as the one with the neutrino.
There will be gamma.
There is a photon. Whenever you have charged particle, you have the photon, so then you're actually going to have a diagram with the photon. And this diagram is much more important than the diagram with the Z because it's low energy. And here you have the propagator, and here we don't. So this one with the photon is going to be much more important.
Low energy, so photon propagator dominates.
Yes. So this will, the photon will be more important. Okay? So it's interesting, but it's not as clean. And when you have the photon propagator, actually the situation becomes a little more complicated. Okay? Good. Anyway, so people went and measured this one. Okay? And in this one, the branching ratio is the same diagram. It's absolutely the same diagram. Because in K long, so here I have SD. And all I care about is the spectator. So I start, let me do it like this. I start with an S and a Q. And this S decay into a D, and the Z decay into two neutrinos. And the Q go like this. So if this Q is equal to a D or a U, okay, so when this is a D bar, that's the K long decay, and when it's a U bar, that's the K plus decay. So you see that this diagram is the same. I don't care about the spectator. Do you see this? So this one, as I said, is a little simpler to measure. So they are already at the level that they see some events. They are not yet at the level that they can say we measure the branching ratio because they don't have enough events. But they are close there. Okay, so hopefully in 2-3 years, we're going to hear from NA62. We have a measurement of the K plus to pi plus nini bar. Okay? And now come the big surprise. Why people are not, why almost everybody sure that Co2 is not this, that there's something big going on. The story is that these two are very, very much related. You see why they are related, right? Because it's basically the same diagram. Yes? Since they are the same diagram, you cannot change this without changing this. That makes sense? Yes? Good? So all you have to do is just say, oh, there must be some relation between those two. Okay? You can then say, if this is the same diagram, these two are related. Okay? And actually one can show, and that's one of my best papers, okay? And it's a trivial paper. It's so trivial, that's why I like it so much. It's just this observation, okay? So one can show that no matter what you do, because of isospin basically, because of this argument, that no matter what physics you have, it doesn't matter really what's going on, there's always this relation that the branching ratio of K long to pi nini bar is actually smaller than some number that people can calculate. It's turned out to be something like 4.1. The branching ratio of K plus to pi nini bar. Okay? It's just this argument. Okay? It's just this argument that I don't care about the spectator. Okay? So then you can just show that this happened. Are you with me on this? Not really. Okay? Yes?
So in this case, you only have the A half amplitude contributing, right?
Exactly. Yes.
But then can't you have an equality like...
So if you have the 3/2, if you have also the 3/2, then this is not correct. But the argument is that it's always, in any new physics, any normal new physics, you must be, the 3/2 is basically suppressed. So it's very similar to what we did yesterday. But I just wanted to tell you that just this simple argument tell you that you have this. Okay?
What contributes to this number?
So it actually has to do with the lifetime difference between those things, and there's some Clebsch of some square root of 2, of some Clebsch. And the square 2 is, yeah. It's easy to, to get those. But I don't want to emphasize too much about what you have here, okay? So the point is that experimentally, if I take this from the measurement, so I take this from this number, and even if I don't really know what it is, I just say what is the maximum I can get from NA62, okay? And I put this number. Let's put a bound on this k long to pi nini bar. And the bound on k long to pi nini bar, it's much smaller than what would happen if you interpret the 4 event of Co2 as a real measurement of k long to pi nini bar. Okay? So basically what I'm telling you is that if you take both Co2 and NA62 and assume both of them see something, then you can actually construct this ratio between the branching ratio of k long and k plus. Okay? And this ratio is actually bigger than this number that I say it's a known number. Okay, it's 4 or something. Okay? So it's basically I'll tell you cannot do it. That's basically the story. Okay? Yes?
This inequality comes from a standard model or from B standard model?
Actually, so this inequality comes from this standard, but actually, and that's the big deal. Okay, that's my paper that I say I like it so much. In our paper, we say it's basically always. Okay? There's some loopholes that you can kind of go around it, but basically, this is very, very generic. It's on any new physics, okay? And I really like it because it's so simple. I really hope you understood what I'm saying, okay? Yes?
If these two processes are related to each other, then is there a lower bound of the k long to pi nini bar?
Exactly. Yeah, so the lower bound on k long to pi nini bar, and I don't remember now the number. What I'm saying is that this lower bound is in disagreement with this result if you interpret this result as a data, okay? And it is in disagreement with something like 2 sigma or 2.1 sigma. That's the point, that 4 event is so large in this case that it violates this bound. It actually tells you that you cannot actually get both of them together.
But is 2 point something sigma actually an anomaly?
As always, there's always this question. I mean, everything here, it's like, 2 sigma, 3 sigma, 4. Nothing is 5 sigma.
Yeah, but...
Yeah. So we always ask the following. We always say this, okay? Let's assume that we do, and then we go through the exercise. But if you say, I only do things that are 5 sigma, then you don't do this, and you go and do dark matter. It's fine. Okay? Which is fine. I mean, there's nothing bad about this. So let me close with my last little story, okay? So this bound, so I did it with my advisor, Yossi Nir. So it's got to know as the Grossman-Nir bound. And actually, it's become really known as, you go to Keon conferences, and you have all this plot, and this line, and it's called the GN bound, or the Grossman-Nir bound. And in the Keon community, everybody knows the Grossman-Nir bound, okay? And a few years ago, I went to some, I think I was in Fermilab, and I met some guy, and I said, what you are doing, and we talked, and I introduced, at some point I introduced myself, I said, you are from the bound? Yes. So it's kind of, so let me close here, and let me kind of summarize where we are on coming back to the big picture. Of course, I could talk forever for so many other things, but what I really want you to understand, remember from these little 5 lectures that I gave, is the standard model is not generic. It's very delicate, okay? And flavor physics are far from generic. And the standard model was built very, very carefully, okay? You have to be very careful. You put your things together very carefully, okay? And if you are not very careful, it breaks down, okay? So now, if you think something is not working, you have to be really careful when you change it, okay? So that's where we are. So we see some anomalies, but it's extremely hard to explain them because the reason that it's so hard to explain them is because the standard model is very delicate and it had been tested so well, okay? So we don't know where we are. We have a very strong theoretical argument why the standard model is not the end of the story, okay? We know that there's something else. And we don't know where we're going to find the entrance to this something else beyond it. And as of now, flavor physics give us a lot of hints. My feeling is those are all false hints called red herrings. They're all red herrings, but I don't know. And, maybe in a few years it will be different. Maybe in a few years I will say, I think this one is very real. And in a few years we will see something. Okay? But until then, we keep, following, working together with the experimentalists and see where we are. And progress in science is not from today to tomorrow, okay? It takes time. And, you look back and it takes time. And when you are in the middle of something, you sometimes don't fully appreciate those things. And only, 10 years from now, you will say, oh, how could I say this? I should have said something different. So the whole point is that I'm telling you guys that, you are younger, some of you were, born after I started doing flavor physics, is that, in this sense, you are in a better situation than I am because you have much longer period to look for those kind of anomalies. And hopefully, maybe some of them will turn out to be real. And maybe we will understand somewhere deeper going beyond the standard model. So that's a good place to stop. Thanks.